Okay, so hello and welcome back. For this particular question, what I want to do is I'm leaving the Doppler effect here. So you can see when the source is moving towards a stationary listener, you can see that the wavefronts become compressed, and when the wavelength decreases, the frequency increases. And similarly, as you move away from a stationary listener, the wavelengths increase, meaning they expand, and therefore the frequency decreases or becomes lower. Now, for the next question, this one's an interesting one because we can reason this out mathematically as well. It says, suppose a train is approaching you as you stand on the platform at the station. As the train approaches the station, it tends to slow down, all while the engineer is sounding the hooter at a constant frequency of 400 hertz. Describe the pitch and changes in the pitch that you hear. Now, we're going to describe those changes in terms of the frequency, right? And so we can see that the hooter has got a constant frequency of 400 hertz. And now, one of the things that you note over there is that this 400 hertz is the frequency of the source. Now, for this particular question, we don't really need to do any calculations. We just need to describe the pitch. Now, if you are stationary, you know that as there's a true constant frequency of the source, which is 400 hertz, right? So for question 3, if frequency of the source is equal to 300 hertz, 400 hertz. That's on me, 400 hertz. Okay. Frequency of the source is equal to 400 hertz. Now, one of the things that you now need to note is the following. If we look at the formula once again of the Doppler effect, right? And in this particular case, we have the source moving, so frequency of the source, VVS over V, and we know that this needs to be greater than 1, so we need the numerator larger than the denominator. So that's the formula you're going to work with. But what I want you to keep in mind is as the train approaches you, the wavefronts are compressed, and hence there's an increase in frequency. So initially, you will hear it, right? I'm going to type that here. Initially, that's a bit extreme. So initially, as train approaches you, okay, as the train approaches you, the listener will observe a frequency higher than 400 hertz. Okay? The listener will observe a frequency higher than 400 hertz. Okay. So, but as the train slows down, okay, as the train slows down, the pitch will gradually, the pitch or the frequency will gradually decrease. Okay, it will gradually decrease until normal spacing. So when I say normal spacing, I mean the wavefronts will be 400 hertz, right? Normal for, yeah. Okay. Let me change this a little bit. The pitch will gradually decrease until it equals a true frequency. Until it equals the frequency of the source when the train stops. Okay, that should clear it up. And I want you to think about this, and if you reason this out mathematically, what you'll come to know is the following. You see, initially, this has got a large value, okay? So when you take this that and that is the same, 340 and this is 340, and let's say this is maybe 50 meters per second, then you're going to end up with 290 here. That means that I've got a number that's going to be significantly larger than 1, which will make FL a lot bigger than FS, right? But eventually when this thing tends towards 0, meaning the train is slowing down, when it's eventually at 0, I have V over V, then the frequency of the listener becomes the frequency of the source, right? So it's going to approach, it's going to appear, you're going to experience it at a higher frequency, but because you're slowing down, eventually the frequency will drop until it becomes the same as the frequency of the source when everything stops. Remember, there's no Doppler effect when there's no relative motion. So that's question 3's answer. Let us go and look at question 4.